Let's continue. Alright, welcome back. Let's continue with our AC power. Right? So we are now at point number 4, which is called power factor correction. Now for power factor correction, it is actually a method to improve the system, to improve the power factor, right? What is power factor? You still remember power factor is cosine theta, right? Now, so basically, this is my O power triangle. PO, QO, and SO, right? And it's a right angle triangle with my theta, right? Which is my O power triangle. Now, when we want to improve the power factor correction, we actually want to make this angle smaller. Right? So my right angle triangle now becomes like this, the angle becomes smaller. Okay? But my new power, my true power, is the same as the O power. In power factor correction, we do not want to change the true power. True power remains the same. So, in order to make the angle smaller, your Q has to reduce. So this becomes the new reactive power. Alright? And this is the new apparent power. Got it? Now then you ask yourself, how do I make my Q to become shorter? Do you introduce a capacitor or do you introduce an inductor? If you recall that inductor is a positive Q, whereas capacitor is a negative Q. So to make it shorter, you actually introduce a negative Q, right? So that when you add on to it QO minus the QC, they become this shorter Q. Okay, so that's why power factor correction is by introduction of a capacitor parallel to the circuit. So this is the original circuit, the circuit, the electrical system. So this is my the voltage supply, and this is my load. So with this circuit, I have my power triangle like this. Now, in order to improve my power factor correction, what I do is that I introduce a capacitor in parallel to the circuit. By introducing a capacitor in parallel to the circuit, I'm introducing a negative JQ. And with that, my Q becomes shorter. Agree? Alright. So now let's talk about the mathematics. Now, the QC, which is the one contributed by the capacitor, do you agree is the QO minus Q nu is equal to QC? Right? And since I know the value, QC can be found. Right? And if you do recall, this is a parallel system. The voltage here is E. What is the voltage here? Also E. So if I were to say this is equal to V squared over XC, right? So V is my E, squared, and my XC is like this. So this is the QC. I already know QC from above. And I know the voltage, I do not know the reactance. So reactance can be found. And we know that the reactance formula is 1 over 2 pi Fc. And if I know the frequency, I know Xc, can C be found? Yes, C can be found. And that is what power factor correction is all about. Right? Simply say, you need an O power triangle, right? And to improve the power factor, is to make the angle smaller. Because cosine theta, the smaller the angle, the bigger is cosine theta. So you make the theta small. But bear in mind that our true power, we want it to remain unchanged. So my new true power is the same as the old true power, but my reactive power now is a shorter one. How to become a much shorter one? Because I'm introducing a capacitor. Capacitor gives me a negative JQ. So QO minus the QC will give me the Q nu. So with this, I get QC. And QC is equal to V squared over XC, I get XC. And XC equal to 1 over 2 pi FC, I get C. Right? Now, you may then ask, why do we need to improve the power factor correction? Now, because in my system here, did I change my voltage? I didn't, right? I didn't change. But you see that SO is actually equal to V times I, right? V times I. And because my V I don't change, this is my O current. mu is equal to V times I as well. And my V is still the same V. Same V, I didn't change. So who changed? My current changed. My current changed. So by improving my power factor, I actually draw out a smaller amount of current. Drawing out a smaller amount of current. And that is what power factor correction is all about. Alright? Okay, we now move on to the last point of AC power, which is called the 2 watt meters measurement. Two watt meters measurement. Now, can you still recall our three-phase circuit? They are the star circuit and the delta circuit, right? So, I give you an example of my star circuit here. So, this is my star circuit. Okay, so this A, this B, this C, and this neutral. And let's say that this 3 plus J 4 ohm. And I know my current here. The current is equal to say 520 ampere. Okay, and then here is 6 plus J 8. Then I know my current here is equal to 15 minus 15 ampere. Okay, and here is equal to 9 plus J 12 ohm, and the current here is equal to 2 minus 40 ampere. Okay. Anyway, all these figures are fabricated. In other words, they may not be true. I just want to illustrate to you. So if I want to find this power here in this system here, I call this is the impedance A, this is the impedance B, and this is the impedance C, right? So if I want the power in the phase A, then I'll say it's equal to I square R. So that is, will be 5 square times 3. Yeah. I want my B, I'll say I square times R. So that will be 2 square times 6. And the C will be I square times R. So that will be equal to 2 square times 9. So the total power, I'll just add it up because I've already found both 3 of them. Am I correct? Now, by doing that, actually, if I were to do this theoretical calculation, I can also use watt meters. Then I need 3 watt meters. 1 watt meters to measure this power here, another watt meter to measure the power here, another watt meters to measure the power here. In this case here, I need 3 watt meters. But we learned that actually, effectively, you can use 2 watt meters to do the job. Okay? When you use 2 watt meters, what it means is that the third one, you use it as a reference. Okay? Let me illustrate. Because in voltage measurement, you always need a reference point, right? A reference point. So if I have a 3-phase system, where this is A, B, and C, phase A, phase B, and phase C. If I have decided that phase B is my reference, then I put my watt meters. In phase A. So this will measure the current, and then this will measure the voltage. The voltage would be reference to the phase that is the reference phase. So since B is my reference, so my voltage I measure is phase A with respect to phase B. The second watt meters, I put it in C. So this is the current coil that measure the current, and this is the voltage coil that measure the voltage. Okay? So this is called wattmeter A, that measure the current that pass through phase A as well as the voltage across phase A with respect to the reference. In this case here, B is my reference. And wattmeter C is measuring the current that goes through phase C and also the voltage with respect to the reference. Alright? Now, with these, 2 wattmeters method say the total true power is equal to WA plus WC. WA plus WC. WA plus WC. And so, the job now is for us to find what is WA and what is WC?